What's up everyone, Patrick here, welcome back. Moving on to the next question. So we got the limit as x approaches infinity of 1 plus 1 over x all to the power of 10x. And this limit here is actually a very popular limit. The result is a very popular one, and I'll expand on talking about that, the different formats that this could potentially be in at the end of the video once we go through the process. But for now, let's just deal with the limit as it's given. So we've got the limit as x approaches infinity. If we do a direct substitution, notice 1 over infinity is going to be 0. So then 1 plus 0 would be 1. And then 10 times infinity would be infinity. So 1 to the power of infinity, notice that that's one of the indeterminate power forms that we went through. And so what you want to do, I went over the process in the overview video, is when you get something like this and it's in one of those indeterminate power formats, you want to take that function that you're working with and convert it to e to the power of ln of that function. Okay, so I did an example in the overview video and I did two methods. They're both the same method. It's just one method we introduced like a y variable and it was a bit longer. In this example, I'm going to be doing that shorter method, but you could do the longer method, follow the exact same steps as well. But what I mentioned is that you first take this function, convert it to e to the power of ln of that same function, and then what you do is you take that limit and you distribute it, quote unquote, to the exponent. Like that. And then what you do is you deal with this limit here separately. So what I'm going to do is I'm going to take the limit as x approaches infinity of ln of 1 plus 1 over x to the power of 10x. And because we ln'd this function, what we could do now is we could bring that exponent down. And so it ends up being 10x times ln of 1 plus 1 over x, like that. And then from here, what I'm going to do, you don't necessarily have to do this, but I'm going to take out that 10. And then I'll have x times ln of 1 plus 1 over x. And what happens here is notice that this would end up being an indeterminate product, because if we plug in infinity for x, we'll have infinity. And then if we plug in infinity for x here, we'll have 1 over infinity, which is 0. 1 plus 0 is 1. Ln of 1 is 0. And so it's an indeterminate product. And so when we get something like that, what we want to do is take one of these functions, bring it to the denominator, and make a reciprocal. So I feel like this one's going to be easier to do that with. So I'll have 10, the limit as x approaches infinity of ln of 1 plus 1 over x, all over 1 over x, like that. And so now if we do a direct substitution, what's going to happen is we're going to have 0 over 0. So we took an indeterminate product, converted it to an indeterminate quotient, where it's 0 over 0. And so with this now, what we can do is apply L'Hopital's rule. And let me just think over here. Yeah, so what I'm going to do, I'll continue this over here. So we'll have 10, the limit as x approaches infinity. So this 10 is staying there the whole time. We factored it out, keep rewriting it on the outside. Take the derivative of this. Now the derivative of ln of a function is 1 over that function times the derivative of that inner function. The derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. All over the derivative of 1 over x is negative 1 over x squared. And now notice this and that cancel out. And so now from here, we could do a direct substitution. Limit as x approaches infinity. If we plug in infinity for x, 1 over infinity is 0. 1 plus 0 is 1. 1 divided by 1 is 1. So this whole thing ends up being 1. And so this ends up being 10. Okay, so this limit here, the final result was 10. We brought down that exponent because we ln'd it, right? We brought down that exponent, factored out the constant, indeterminate product, converted it to an indeterminate quotient, applied L'Hopital's rule, and then simplified it, and we end up getting 10. So the result of that limit is 10, but that's not our final result. Because remember, we're working with this main limit here. This was sort of work on the side to figure out what's that limit in the exponent. And we know that that limit in the exponent is equal to 10. And so what happens is that ends up being our final answer, e to the power of 10. So the limit of this over here is e to the power of 10. And in fact, whatever number this is, we could convert this to like an m, let's say, where m is just any real number. And the limit of that is always just going to end up being e to the power of m. In this case, it was 10, but that could be anything. Another popular limit you'll sometimes get is where that m is 1, where you'll just have an x there. So there's like an imaginary 1 there. And so the final result of that would just be e to the power of 1, which is just e. Okay, so whichever limit you're given, whatever m value that is, you'd end up with e to the power of that m value. Just make sure it's got to be in this exact format. It's not always going to be. There's so many different types of limits that you can get, but a lot of times this is a popular limit that comes up, right? So quick review, took that function, converted it to e to the power of ln of that function, distributed that limit using the properties of the limits to the exponent, and then we worked with that limit on the side. Because we ln'd this, we were able to bring that exponent down, indeterminate product, converted it to a quotient, L'Hopital's rule. That whole limit ended up equaling 10. And so the final answer is e to the power of 10.